Welcome to the Introduction to Battery Technology course. This lecture focuses on Chapter 4, which discusses nickel-cadmium batteries. Today, we're starting Chapter 4 on nickel-cadmium, or NICD batteries. Our learning objectives are straightforward. First, we'll gain an overview of NICD batteries, including their operation, key performance characteristics, and other relevant details. Second, we'll look at where NICD batteries fit compared to other technologies you might see in the plant. Before we dive into the details, here's a bit of history. The NICD battery was invented in 1898 by Ernst Waldemar Jungner, a Swedish engineer. Not only did he create the NICD battery, but he also invented the nickel-iron battery and a silver-cadmium rechargeable battery. Pretty amazing, considering most of us are still figuring out how to keep our phones charged all day. On the slide, you'll see two pictures of NICD batteries. One shows a real cylindrical cell like you might find in tools or equipment, and the other shows the inside structure. Don't worry, we'll go into detail about each component in the next few slides. For now, just remember, NICD batteries are one of the oldest rechargeable chemistries, yet they are still valued for their durability, long cycle life, and ability to withstand tough conditions. So, let's get started with what makes these batteries unique. On this slide, we're focusing on some key terms you'll encounter with nickel-cadmium NICD batteries. I would like to highlight one term in detail today: electrochemical reactions. These are the chemical processes inside the battery that let electricity flow. In NICD cells, the positive electrode is nickel oxyhydroxide, NiOH, and the negative electrode is cadmium, Cd. During discharge, nickel oxyhydroxide is reduced to nickel hydroxide, while cadmium is oxidized to cadmium hydroxide. This transfer of electrons is what generates an electric current. Now, here's the important part. The voltage of 1.2 volts per cell comes directly from chemistry. The standard electrode potential for the nickel oxyhydroxide/nickel hydroxide couple is about plus 0.49 V. And for the cadmium/cadmium hydroxide couple, it's about minus 0.76 V. The difference between these two values yields approximately 1.25 V, which rounds to the familiar 1.2 V per NICD cell. So that number isn't random, it's baked into the physics and chemistry of the materials themselves. The other terms on this slide, overcharge, capacity, energy density, battery stack, are also important, but don't worry if they don't stick yet. We'll see them again and again as we go deeper into battery technology. Finally, take a quick look at the images of nickel, Ni, atomic number 28, and cadmium, Cd, atomic number 48, from the periodic table. This is a reminder that battery technology is grounded in the elements themselves. Whenever you work with a battery, it's always worth asking, where do these elements sit on the periodic table? And how does their chemistry set the rules for the battery's performance? The key takeaway here is that batteries work due to electrochemical reactions. The voltage per cell is fixed by the electrode material's natural potentials, in NICD's case about 1.2 V, and the vocabulary we'll be using is all tied to these fundamentals. When considering NICD batteries, it's essential to strike a balance between their strengths and weaknesses. Let's break it down. Advantages. One of the biggest strengths of NICD batteries is their high cycle life. With proper use, they can last thousands of cycles, sometimes over 5,000 if managed at partial depth of discharge. This makes them very durable compared to many other chemistries. Another highlight is their stable discharge voltage around 1.2 volts per cell. That means devices powered by NICD run very consistently until the battery is nearly empty, unlike some batteries where power fades quickly. Disadvantages. On the downside, NICD batteries suffer from the memory effect, meaning they can lose usable capacity if not fully discharged periodically. This makes maintenance important. And probably the biggest challenge today, cadmium is toxic and environmentally harmful, which is why NICD batteries are now restricted or banned in many regions, especially the EU. So, in summary, NICD batteries are rugged and reliable performers, great for cycle life and stable power, but they come with environmental and maintenance challenges. Now let's take a closer look at what makes up a nickel-cadmium NiCd battery. When the battery is fully charged, the cathode is made of nickel oxyhydroxide, or NiOH. The anode is cadmium metal Cd. In between, the electrolyte is a solution of potassium hydroxide, typically 20 to 30% mixed with water. Notice that the electrolyte itself doesn't really change. It acts more like a medium that allows ions to move around. When the battery is fully discharged, the cathode changes into nickel hydroxide, NiOH2, and the anode becomes cadmium hydroxide, CdOH2. But here's the important part. The electrolyte stays the same, still KOH and water. That's different from lead-acid batteries, where the acid concentration changes a lot during charging and discharging. Think of it like this. If a lead-acid battery is like a soda that gets watered down as you drink it, an NiCd battery is more like a reusable cup of water. The liquid is always there, but the flavor changes at the electrodes. We'll go deeper into how these reactions happen in the next slide. But for now, just remember, NiCd's active chemistry is in the electrodes, while the electrolyte remains stable. That's one of the reasons these batteries are very robust and can withstand numerous cycles. Now let's look more closely at how a nickel-cadmium battery is built and how it works during discharge. On the positive side, or the cathode, we have nickel oxide hydroxide, NiOH. On the negative side, or the anode, we use metallic cadmium, Cd. The electrolyte is a 30% potassium hydroxide, KOH, solution in distilled water. Notice that the electrolyte here is different from what we saw in lead-acid batteries. It's alkaline, not acidic. That's why NiCd cells are sometimes referred to as alkaline batteries. One key point: the electrolyte does not change composition during charge or discharge. Its job is just to conduct ions between the electrodes. That's very different from lead-acid batteries, where the acid concentration itself changes, and we can measure specific gravity to check charge level. With NiCd, you don't get that direct indicator. Looking at the diagram, you can see the cathode, NiOH, and anode, Cd, sitting in the KOH electrolyte, separated by a porous separator to prevent short circuits. When the battery discharges, electrons flow from the cadmium anode to the external circuit, powering a device like lighting the bulb in this picture. In short, NiCd batteries rely on a stable alkaline electrolyte and robust electrode chemistry, which provides them with long cycle life and durability. On this slide, we see how a NiCd battery works during discharge and charge, summarized in the table. During discharge, at the anode, cadmium, Cd, is oxidized to cadmium hydroxide, CdOH2, releasing electrons. These electrons travel through the external circuit to power a device. At the cathode, nickel oxyhydroxide, NiOH, reacts to form nickel hydroxide, NiOH2. This balances the reaction by consuming and regenerating hydroxyl ions, OH, from the electrolyte. During charging, the reactions reverse. The cathode regenerates NiOH from NiOH2, and the anode converts CdOH2 back into metallic cadmium. Essentially, the battery is restored to its original state, ready for another cycle. The chemical reaction at the bottom ties everything together. 2 NiOH plus Cd plus 2H2O2 NiOH2 plus Cd OH2. The double arrow shows that the reaction is reversible, which is what makes the NiCd battery rechargeable. Key takeaway: NiCd batteries rely on a reversible exchange between nickel and cadmium compounds, with the electrolyte, KOH plus H2O, serving as the medium but not being consumed. That's why NiCd cells can go through thousands of charge/discharge cycles. This slide shows the schematic diagram of the discharging and charging of a NiCd battery. We have two diagrams that make the chemistry we just saw in the table more visual. On the left, we see what happens during discharging. The cadmium anode gives up electrons, which travel through the external circuit to power a device, here shown as a light bulb. Meanwhile, the nickel oxyhydroxide at the cathode reacts with water, forming nickel hydroxide and balancing the charge. The electrolyte, which is potassium hydroxide, mainly acts as a medium for ion transport and doesn't change much chemically. On the right, we see the charging process, which is basically the reverse. By applying an external power source, electrons are pushed back into the cadmium electrode, reducing cadmium hydroxide back to metallic cadmium. At the same time, nickel hydroxide is oxidized back to nickel oxyhydroxide at the cathode. The system resets, ready for another discharge cycle. So in simple terms, discharge equals battery powering your device, electrons flow out. Charge equals power supply pushing electrons back in. Discharging process. This diagram illustrates the detailed chemical reactions that occur within a NICD battery during discharge. On the anode side, metallic cadmium, CD, reacts with hydroxide ions, OH, from the electrolyte, forming cadmium hydroxide, CD, OH2, and releasing 2 electrons into the external circuit. These electrons provide the electric current that powers a device. On the cathode side, nickel oxyhydroxide, NiOH, combines with water and the incoming electrons to form nickel hydroxide, NiOH2, and hydroxide ions, OH. The overall reaction balances neatly. CD plus 2 NiOH plus 2 H2O CD, OH, 2 plus 2 NiOH, 2. Notice that the electrolyte KOH is not consumed in the reaction. It acts as a medium for ion transfer, which is why the concentration remains almost unchanged during cycling. The key takeaway for technicians: electrons move outside the battery, ions move inside, and the chemistry ensures a stable 1.2 to 1.3 V per cell output during discharge. And here's a fun way to think of it. Cadmium is like the worker donating electrons, and nickel is like the collector taking them in to keep the light bulb on. As we wrap up the principle of operation of NICD batteries, here is a one-sentence summary for both the charging and discharging processes. During discharge, cadmium releases electrons and nickel oxyhydroxide accepts them, producing a steady 1.2 to 1.3 volts per cell while the electrolyte KOH stays unchanged. During charging, an external power source drives electrons back into cadmium hydroxide and nickel hydroxide, restoring them to cadmium and nickel oxyhydroxide, ready for another discharge cycle. Let's talk about what happens when a NICD battery is overcharged. When the battery is already full, continuing to push current into it doesn't store more energy. Instead, electrolysis of water begins. The cathode produces oxygen gas, and the anode normally produces hydrogen gas. This gas generation increases both pressure and temperature, which can be dangerous. Now, to make sealed NICD cells safer, engineers actually oversize the negative electrode. Why? Because it prevents the anode from reaching full charge. That means the cathode finishes charging first and starts producing oxygen before hydrogen can be formed at the anode. The oxygen then reacts chemically with cadmium hydroxide at the anode, creating a kind of self-balancing cycle. In this way, hydrogen production is suppressed and pressure stays under control. In simpler terms, the cell is designed so that only oxygen builds up first, and that oxygen gets recycled back into the chemistry. This is why sealed NICD cells can handle some overcharging without exploding. If you look at the photo here, you can see what real overcharge stress looks like. The ammeter indicates a significant current, the electrodes are glowing, and you can even see the gas being released. This is a stark reminder. Excessive overcharging leads to heat, pressure, and ultimately damage. The key takeaway is that NICD batteries have built-in mechanisms to handle mild overcharge, but in real-world operations, overcharging must be avoided because in the long term it still reduces battery life and can create safety risks. On this slide, we see a diagram that illustrates what happens inside a NICD battery during overcharging. When the battery is pushed beyond full charge, the cathode starts producing oxygen before the anode is fully charged. To control this, NICD cells are designed with an oversized anode. The extra size allows the anode to continue reacting with oxygen to form cadmium hydroxide, which is then electrochemically converted back to cadmium. This creates a repeating cycle, shown in the diagram, where oxygen is continuously consumed. Notice the gray portion in the anode. This represents the extra electrode material that makes this balancing act possible. Thanks to this design, the pressure inside the sealed cell is kept under control, preventing the battery from swelling or venting dangerous gases. The key takeaway here is that NICD batteries handle overcharge better than many other chemistries, but this is achieved through a clever self-balancing reaction between oxygen and cadmium hydroxide. Still, too much overcharging generates heat and stress, so protection circuits or careful charging are always important. Overcharging is one of the most critical issues in NICD batteries because it leads to unwanted gas generation. Inside the cell, the recombination process sometimes cannot keep up with the charging current, which causes pressure and heat to rise. In vented cells, overcharging splits water into hydrogen and oxygen. These gases are released through vents, but the water is permanently lost. If water isn't replenished in time, the battery loses capacity, overheats, or suffers permanent damage. In sealed cells, the gases cannot escape. Pressure builds up inside, and if the design or safety features fail, the battery may rupture or even explode. This is why sealed cells need very careful charge control and built-in protections. Remember, overcharging not only shortens battery life, but can also create serious safety hazards for workers and equipment. Now, before we continue deeper into the technical aspects, let's take a short pause and look at something a bit lighter but still meaningful. The quotes you see on this slide are from Nickel Metal Hydride, an overview on Science Direct topics. Let me read them for you. Nickel-Cadmium NICD batteries are renowned for their impressive energy density, enabling them to store a substantial amount of energy in a compact form. Additionally, NICD batteries are able to deliver reliable performance in even the harshest conditions, whether it's extreme temperatures, high humidity, or challenging terrains. The source here is Science Direct, a trusted academic and technical reference site. The article highlights why NICD batteries remained important for so many years, despite the emergence of newer technologies. You'll also notice the two images on this slide. They remind us of the locations of nickel and cadmium on the periodic table. Nickel is element 28, with an atomic mass of 58.6934, and cadmium is element 48, with an atomic mass of 112.41. And here's the interesting part. The well-known 1.2 volts per cell of a NICD battery isn't an arbitrary number. It comes from the difference in the standard electrode potentials of the two reactions. Nickel oxyhydroxide, NiOH/NiOH2, has a potential of about plus 0.49 V, while cadmium, CD/CD, is around minus 0.76 V. When you take the difference, you get roughly 1.25 V, which in practice gives us the stable 1.2 V per cell that NICD batteries are famous for. So, when you see those numbers on the periodic table, the atomic numbers and masses, remember they're not just chemistry trivia. They connect directly to why these elements behave electrochemically the way they do, and why NICD batteries can reliably deliver their characteristic 1.2 volts. On this slide, we examine how NICD batteries are charged, and one key concept to understand is the C rate. The preferred charging method for NICD batteries is to start with a high current, between 1C and 6C, until approximately 70% of the battery's capacity is reached. After that, the current is reduced to safely complete the charge. For example, at 4C, you could fully charge a battery in about 10 to 15 minutes. That sounds great, but there's a catch. The heat produced at 4C is 16 times greater than at 1C. That means temperature, voltage, and pressure must all be closely monitored to avoid overcharging or dangerous conditions. Now, let's break down the C rate equation. The C simply stands for capacity. A 1C rate means you're charging or discharging at a current equal to the battery's rated capacity. So, if you have a 10 amp battery, charging at 1C means a 10 amp current, and the battery would charge in about 1 hour. If you increase the rate to 4C, you're charging at 40 amps, so the charge happens much faster, but with much more heat and stress on the battery. So, the key takeaway: high C rates equals faster charging, but also higher heat and more risk. This is why control systems are absolutely necessary in real-world battery applications. On this slide, we look at how voltage, temperature, and pressure change as a NICD battery charges. At the beginning of the charge, there is a rapid spike in cell voltage. That's the battery responding quickly to the incoming current. After this spike, voltage, temperature, and pressure increase more slowly as the battery continues to accept charge. However, once the battery reaches full charge, the behavior changes dramatically. The cell voltage rises more sharply as the electrochemical reactions shift to side reactions. At the same time, temperature and internal pressure rise rapidly. This is the danger zone for overcharging. This graph serves as a clear reminder. Monitoring voltage, temperature, and pressure during charging is crucial. In production or maintenance, if you see unusual jumps in temperature or pressure, that's a red flag. It means the battery is no longer charging efficiently. It's heading into overcharge, which can damage the cell or create safety risks. Now, let's examine how we actually determine the charge level in a NICD battery. Unlike some other batteries, you cannot simply measure a single voltage or temperature value to determine exactly how full the battery is. Instead, we rely on several methods combined. The most common method is to watch for a voltage drop at full charge. As shown in the left-hand graph, the voltage rises during charging, but at full charge, there's a slight dip, indicating that the battery is fully charged. Another method is to monitor the rate of temperature increase, shown in the right-hand graph. As the battery reaches full charge, heat starts building up quickly, so a sharp rise in temperature is a strong indicator. Other techniques include measuring the absolute temperature itself or using timeout timers to stop charging after a safe period. In practice, chargers usually combine two or more of these methods to avoid overcharging and overheating. The key takeaway is that NICD charging is not as simple as looking at one number. You need to track multiple signals to charge safely and effectively. Here we see the discharge curve of a NICD battery. Notice how the voltage stays very stable around 1.2 volts for most of the discharge. This flat region is one of the strengths of NICD batteries. It provides consistent power output until nearly the end of the cycle. Once the cell is nearly empty, the voltage drops sharply to approximately 0.9 volts, marking the end of discharge. In practical terms, this means devices using NICD batteries can run steadily for most of their runtime and then quickly lose power at the end, rather than fading slowly. This graph illustrates the variation in NICD battery capacity with discharge current. Notice that as the discharge current increases, the available capacity decreases. This is due to internal resistance and chemical limitations. Interestingly, when the discharge current is less than the nominal 1C rate, the effective capacity can actually appear higher than 100%, because the battery has more time to fully utilize its active material. In practical terms, this means that devices drawing lower current can achieve longer runtime from the same battery compared to high-power applications. This graph illustrates the impact of temperature on the discharge performance of NICD batteries. At higher temperatures, such as 20 degrees Celsius, the battery maintains a higher voltage and delivers more capacity. As the temperature drops, especially down to -20 degrees Celsius, both voltage and usable capacity decrease significantly. In other words, NICD batteries work much better in warm environments than in very cold ones. This is why, in real applications such as outdoor equipment, temperature control is critical to ensure stable performance. In summary, NICD batteries maintain a stable voltage of approximately 1.2 V during discharge. However, their capacity decreases with higher discharge currents and lower temperatures, illustrating the direct influence of both load and environment on performance. Now let's talk about a very dangerous condition in NICD batteries, polarity reversal. This happens when a battery is overdischarged, meaning we keep pulling current from it even after it's already empty. In a battery stack where cells are connected in series, this usually happens because not all cells are identical. Some cells may have slightly lower capacity, higher resistance, or a weaker voltage than others. When that weaker cell reaches its cutoff voltage of 0.9 volts, it should stop. However, because the other cells in the series are still running, the current continues to flow through it. The weak cell is then forced to continue discharging, and instead of working normally, its polarity actually flips. Its positive electrode becomes negative. That's like suddenly wiring the cell backwards inside the pack, which is very harmful. This is why chargers with reverse polarity protection, like the circuit diagram you see here, are so important. They don't just charge the battery. They also act as a safeguard, preventing current from flowing the wrong way and protecting both the battery and the equipment. Think of it like a one-way valve in plumbing. It makes sure electricity only flows in the safe direction. When a polarity reversal happens, it's not just a minor issue. It can create serious problems inside the battery stack. If one weaker cell in a series string gets pushed too far, it can flip its polarity. This leads to pressure buildup, potential short circuits, and, in the worst case, damage to the entire battery pack. Once polarity is reversed, the cell's chemistry is thrown off balance, which can create hazardous conditions such as overheating or venting gases. To help control this, manufacturers add a small amount of CdOH2 to the cathode. This antipolar mass acts like a safety buffer, slowing down oxygen gas generation during overdischarge. It's not a perfect solution, but it helps mitigate the danger when mistakes occur. Now, the good news is that most polarity reversals can be prevented with good battery care practices. Avoid deep discharges. Stop using the device when the voltage gets low instead of pushing it until it dies. Use smart chargers. They have built-in protections to prevent wrong connections. Store batteries correctly. Cool, dry places work best. If long-term storage is needed, never short-circuit the cells. Occasional conditioning for NICD. Some users recommend a controlled deep discharge every few months to keep cells balanced. On the factory floor, this means keeping a close eye on both equipment and batteries. Don't ignore low-voltage warnings. Don't mismatch cells of different ages or conditions in the same pack, and always follow the correct charging procedure. These simple steps can prevent expensive damage and keep both workers and equipment safe. This graph illustrates the effect on the voltage of a single NICD cell when polarity reversal occurs during deep discharge. First, the positive electrode flips polarity, causing the cell to drop below 0 volts. If discharge continues, both electrodes reverse polarity, driving the voltage even further negative. This process not only damages the individual cell, but can also compromise the entire battery stack. That's why preventing deep discharge is so critical for both performance and safety. Now let's talk about one of the biggest strengths of nickel-cadmium batteries: their cycle life. The graph you see illustrates the relationship between the depth of discharge and the number of cycles a NICD battery can withstand. What stands out here is that NICD batteries can survive thousands of charge-discharge cycles, far more than the other main types, such as lead-acid, NIMH, or even many Li-ion cells. Why is that? Stable chemistry. The reactions between nickel and cadmium remain very reliable even after long use. Deep discharge tolerance. Unlike other batteries, NICD can be fully discharged without serious damage. Overcharge resistance. They can withstand occasional overcharging, which enhances their robustness. Durability. They perform well under stress, whether it's extreme cold, high heat, or high discharge rates. In practice, this means a typical NICD battery can last 1,500 to 2,000 cycles, and with good care, even more. That's why they were historically chosen for applications where long-term reliability was more important than weight or size, such as aviation and backup power systems. So, if there's one takeaway here, it's this: NICD batteries may not be the most energy-dense, but when it comes to longevity and toughness, they're among the best. Now let's talk about one of the biggest drawbacks of NICD batteries: self-discharge. These batteries lose energy even when they are just sitting on the shelf. In fact, within the first 24 hours, they can lose about 10% of their charge, and after the first month, nearly 20% is gone. After that, the average rate is approximately 10% loss per month at room temperature, 20 degrees Celsius. The graph here illustrates the significant impact of storage temperature. At 0 degrees Celsius, capacity is retained much longer, But as the temperature increases, the self-discharge accelerates. At 40 degrees Celsius, the battery can lose all of its capacity in just 2 months. This is why proper storage is critical. To manage this issue, we use trickle charging, a very small continuous charge, or store the batteries in a cool, dry place. These simple steps can significantly extend storage life and keep the batteries ready for use. On this slide, we examine one of the well-known issues in NICD batteries, the memory effect. This phenomenon refers to a loss of usable capacity when the battery is repeatedly discharged only partially, rather than fully. The unused active material inside the cell starts to form cadmium hydroxide crystals, shown in the images here. You can see the crystals growing larger over time, from about 1 micron to several microns and eventually to 100 microns after about 3 months. This crystal growth reduces the effective surface area of the active material, thereby lowering the battery's performance and giving the impression that it remembers a lower capacity. Typically, irreversible growth begins after 6 to 8 weeks of repeated partial discharges. To prevent this, manufacturers and users often recommend performing a full discharge and recharge cycle about once a month. The key takeaway here is that while NICD batteries are durable and long-lasting, they require occasional conditioning to reset their memory and restore optimal performance. Together, the memory effect, cycle life, and self-discharge remind us that while NICD batteries are durable and long-lasting, their performance ultimately depends on how they are charged, discharged, and maintained over time. This concludes Chapter 4 of the Introduction to Battery Technology course. For deeper insights, please refer to the references provided on this page and consult the textbook to further solidify your understanding of the concepts introduced in this chapter. Once you feel confident with the material, you are encouraged to explore the additional resources available in this module, including the lecture presentation, recommended YouTube videos, and supplementary readings. These will help you reinforce your knowledge before moving on to the practice exercises and, ultimately, the end-of-module assessment. Thank you. We'll meet again in the next lecture. Thank you. We'll meet again in the next lecture.